The problem we're looking at now is an inquisitive physics student and mountain climber climbs a 50-meter high cliff that overhangs a calm pool of water. He throws 2 stones vertically downward, 1 second apart, and observes that they cause a single splash. The first stone has an initial speed of 2 meters per second. A. How long after release of the first stone do the 2 stones hit the water? B. What initial velocity must the second stone have if the 2 stones are to hit the water simultaneously? And C. What is the speed of each stone at the instant the 2 stones hit the water? Take a few minutes and draw a picture of the situation, label all your knowns and your unknowns. Your diagram should match what I've put up here. We have, of course, the initial time for particle 1 and 2. We do not know the initial velocity of particle 2. We know the initial velocity of particle 1. We know the initial height from which each one is dropped. We know the final height, we can just call that 0. And we know that the final time of each particle is the same. What other information do we have? Once again, pause the video and consider the fact that they made the splash at the same time indicates, of course, what we've already stated, that T1 is equal to T2 final. And of course, we also know that the second stone is dropped 1 second later than the first stone. So the question becomes, do I have enough information to calculate the fall time required for one of the particles? Pause the video and determine if you do. Well, let's think about what we know about the first particle. We know the initial position. We know the final position. We know the initial velocity. And we know the acceleration. So is there enough information to calculate the time of fall for that first particle? Is there a relationship or equation that involves all these knowns and the time? Take a few minutes and write down your equation. There is an equation, YF, the final position, equal to the initial position plus the initial velocity times the time plus 1/2 the acceleration times the time squared. In this case, since we're dealing with free fall, we're going to have A will be equal to minus G. As far as our variables, we know that y f is 0, y I is equal to 50, we know that VIY is equal to a minus 2 meters per second, taking the downward direction as minus, and A will be equal to minus 9.8. Plugging in those numbers, I obtained the quadratic equation 4.9 t squared plus 2.0 t minus 50 equals 0. Go ahead and solve the quadratic equation. You should obtain 2 times. Go ahead and pause the video, get your solution, and then I'll write down my solution. Using the quadratic formula, which we recall is that t will be equal to minus b over 2a plus or minus square root b squared minus 4ac over 2a, gives us that t will be equal to 2.996 seconds minus 3.404 seconds. Of course, this is the intercept where t is equal to 0, or where y is equal to 0. Of course, our solution is the positive square root, so the answer to part A is that t equal 2.996 seconds for the first particle. Now the question becomes, what is the fall time of the second stone? Well, the first stone, T1, was equal to 2.996 seconds. Therefore, the second stone is simply T1 minus 1 second, which is equal to 1.996 seconds. The question now is asked, what is the initial velocity that the second stone must have? Well, what do we know about the second stone? We now know the time of fall, the acceleration, the initial position, and the final position. So the question becomes, with that information, do we have an equation that contains all those variables except including the initial velocity and the initial velocity as the unknown? Pause the video and write down the equation you think is going to work. Once again, we can go back to the following equation. Final height equal to the initial height plus the initial velocity t times the time of fall plus 1/2 a t squared, where of course now VIY is our unknown for the second particle. So now let's solve algebraically for VIY. That's simply going to be equal to YF minus YI minus 1/2 a t squared over t will be equal to VIY. Or now we'll put in for A equal to minus 9.8 meters per second squared. Go ahead and work it out and get the solution. Pause the video. I obtain for VIY is equal to a minus 15.3 meters per second. Okay, now we're asked the second, or the part C, what is the speed of each stone the instant the two stones hit the water? Well, now we have the following information: the initial velocity of each stone and the time through which each stone falls. Is there a relationship that I can use to calculate the final velocity of each stone? And pause the video and write down the relation. We do have a relation. The final velocity is equal to the initial velocity plus a acceleration times the time through which the acceleration occurred. In this case, V1 YF equal to VIY1 minus 9.8 times t. Well, we know what that is, so that means that V1YF will be equal to minus 2.0 minus 9.8 times 2.996 seconds. And that's going to be equal to 31.4 meters per second. Likewise, V2YF will be equal to minus 15.3 meters per second minus 9.8 times 1.996 seconds, and that will be equal to 34.8 meters per second. End of problem.